All right, so we began chapter 2 today, and the big essential question that I want you to focus on for the entire chapter is, how does algebra help explain? And we started off today with some patterns that will actually show you how algebra begins to help explain things. So we started with using the chips, the circles, and this is what we found when we looked for a pattern. So first of all, I had you just investigate where you saw the figure number in the figure itself, and right away you guys noticed that there were 4 chips in the bottom row of the 4th figure, and 3 chips in the bottom row of the 3rd, and 2 chips in the bottom row of the 2nd, etc. So at your table groups, you built the 5th figure with the yellow chips, you put 5 in the bottom row, and then all 10 of these were above those 5, because above the 5 goes 4, 3, 2, 1, which was the 4th figure, 4, 3, 2, 1. So really what you guys discovered was that the 5th figure number has a total of the 4th figure number, those 10, from the previous figure, plus 5 new ones, and 10 and 5 is 15. And then you found that, gee, the 6th figure number will have 6 new chips on the bottom, plus all of the 5th figure's number on top here, those 15, and 15 and 6 is 21. And then you ended up following the pattern, and you found the 7th has 28, which is all of the 21 plus the new 7 on the bottom. The 8th figure has 36, which was all of the 28 plus the new 8 at the bottom, etc. And the big idea was how many would be in the nth figure number, because we're looking for an algebraic pattern here. And so I had you put 2 of your triangles together. I showed you with the table group in the front of the room, and we shoved one triangle from one side, Alyssa's, over to Sarah Neig's, and we found that we got a rectangle, that the 5th figure number was 5 by 6, which is 5 by 1 bigger than 5. And then we found that, whoa, 5 times 1 bigger than 5 is 5 times 6 is 30, and that the number of chips is half of that, because remember, half of this was Sarah's and the other half was Alyssa's. And so what we found is that the 6th figure would be a rectangle that's 6 by 7, and 6 times 7 is 42, and half of it is 21. And the 7th would be a 7 times 8 rectangle, which is 56, and half of 56 is 28. So the nth figure would have a dimension of n by n plus 1, and that we multiplied them together to get the area of the rectangle, and then we have to divide by 2 because it's a triangle and we want half of each person's. So the 125th figure number, how algebra helps you explain, is if this is n, it's the width of the rectangle, and if this is n plus 1, it's the length of the rectangle. This would be the 125th triangle here. And so when we put 2 of them together, we get a rectangle that's 125 by 126. And now you can just pop that in your calculator, multiply 125 by 126, and divide it by 2. And we have actually the number of chips that I would need for the 125th figure number. So we did it for the 100th, and you found it was 100 times 121 divided by 2, and that was 5,050 chips. So that pattern, n times n plus 1 divided by 2, helps you explain the entire pattern for triangular numbers. So algebra helps you explain. And then we looked at it as if we were going to graph this with a set of ordered pairs, and we see the same. We could graph this. These would be ordered pairs, and we would see that we get a curve, which would look like a parabola. All right, and then we started off this unit with a card trick, and I did the card trick with you guys. If you want to remember what it was, it's on pages 64 to 65, and it's just algebra in disguise. So algebra helps explain and describe the card trick. And then we began using some algebra tiles, and remember, algebra tiles are just a manipulator that helps you see the abstractness of algebra. So we had a little 1 by 1 centimeter tile, and we named the tiles by their areas, and 1 times 1 is 1, so these are 1 tiles. And then you had rectangular tiles that are 1 by an unknown length, and 1 times x is x, so these are called x tiles. And then there are big squares that we really didn't use today. We'll use them next class, but they are x by x. They are this length and then the same width, and x times x is x squared, so we call these big squares x squared tiles. Now the purpose of these is to help you understand the distributive property today. So I had you build 3 groups of x plus 2. This is an x tile plus 2, so here's one group of x plus 2, another group of x plus 2, and a third group of x plus 2. And so if I want to get rid of the brackets, I want to expand 3 groups of x plus 2. Okay, I just rearrange them. And I can see that if I take all of the x's and put them together, I get 3 of them. And I take all of the 2's and put them together, and I get 6. So the distributive property simply says that 3 groups of x plus 2 is the same amount as 3 x's plus 6. So to get rid of the brackets is called expanding this, and it's literally where I just multiply 3 times x plus 3 times 2, because you can see I have 3 groups of all of x plus 2, 3 x's and 6. And then I had you use tiles and show me 2 groups of x plus 4, and you guys did get 2x plus 8. And then we talked about with negative numbers, if I have 5 groups of x minus 4, remember x minus 4 is the same thing as x plus a negative 4. So you can do this in 2 ways. You can simply distribute and multiply. Multiplication over subtraction, 5 times x is 5x. Bring down the subtraction sign, and 5 times 4 is 20. Or you can think of this as 5 groups of x plus a negative 4, and you get the same answer. That's 5x's plus a negative 20, and 5x plus a negative 20 is 5x minus 20. Same answer here, same answer here. And then we took a real example. So I have a theater. There are 10 seats in each row, and maybe this is at an opera house. The first 3 rows are more expensive, and the next 5 rows are cheaper because they're further away from the audience. So for you to see, I can look at 2 ways of counting all the seats. I can treat all the rows alike and say I've got 10 seats, 10 seats, 10 seats 8 times, so I can do 10 times the 8 rows and get 80 seats. Or I can count the expensive seats separately and the cheaper seats separately and add the result. So I've got 3 times 10 or 30 seats, plus 5 times 10 or 50 seats, and if I add those, I get 80 seats. That's also the distributive property. 10 times 8 is 80, which is just like 10 groups of 3, and 10 groups of 5, 30, and 50 is 80. So I can either just do 8 times 10, or I can do 30 plus 50. Both will give me 80. And then we looked at it in terms of an algebraic form of the property. C times the quantity of A plus B is the same as C times A plus C times B. And then how is this similar to the algebra tiles? Well, 3 times x plus 2. So if C is 3 and x is where A is and B is 2, this is the same thing as my 3 x's and my 6 1's. In terms of the theater rows, it's just like 10 groups of 3 plus 5 is the same as 80, or the same as 30 plus 50, which is also 80. So just vocabulary, getting rid of the brackets is called expanding. So when I distribute my 3 to my x and my 2, I expand the expression to get 3x plus 6. And then we just did an example with Michael here. So he charges X dollars for walking a small dog, and Y dollars for a medium dog, and Z dollars for large dogs. Every day he walks 2 small dogs, 1 large and 1 medium. So that's 2x plus Y plus Z. So then I said, how much money would he make in 7 days? So we put brackets around it, and we had to distribute our 7 to the 2x. 7 times 2x is 14x. Plus 7 groups of the Y money, plus 7 groups of the Z money. So because he walks 2 dogs, he's going to get paid 14 times what he gets paid for a small dog in a week, and he only walks 1 medium dog, so he'd get paid that 7 times, and 1 large dog, so he'd get paid that 7 times. And then distributive property was really helpful to compute mentally. For example, suppose a motel room is $89 a day and you're staying for 4 days. Well, multiplying 89 times 4 in your head isn't as fast of thinking of 89 as 90 minus 1, because I can do 4 times 90 mentally very easily, 360, and then 4 times 1 is 4, and subtracting 360 minus 4 is very easy, so I get 356. Or I'm going to pay €199 9 times. Well, it's easier to think of 199 as 200 minus 1, because 200 times 9 is easy to compute mentally, 1800, and I'm short 209 times by €1, so I've got to subtract that 9, and I get 1,791 euros. So using the distributive property helps you compute mentally, with subtraction especially. And then we talked about the ways that Distributing multiplication over addition is the same as multiplication over subtraction. And you guys said they've got the same letters. You multiply C by A and B the same way each time. It's just that in these two you would add, and in these two you would subtract. We practice some. So this becomes negative 11 times 5, which is negative 55. And negative 11 times negative 6x is a positive 66x. If you want to rewrite it as addition first, you may, but you can just distribute negative 11 to each term. Link this subtraction with the 6x so you see it as a negative 6x, and then your negative times a negative is a positive. And then we practice expanding when I have 2x times 5x. Remember, x times x is x squared. So I literally have 2x times 5x, which you can rewrite. Put the numbers together. 2 times 5 is 10. X times x is x squared. So 2x times 5x is 10x squared. And 2x times 3 is 6x. And that's the best I can do. I can't simplify these anymore. These are 10 of the big x squared tiles, and these are 6 of the rectangles. And I can't put those together. So this is as simplified as I can get that, because these are different size tiles. So this rectangle is 5x plus 3 long, which is this length, and 2x wide. And if I fill it in with the tiles to make a rectangle, you can see the 10x squared here and the 6x is here. And to simplify a fraction, remember this is a grouping symbol, so I must distribute the 3 to each term. I have to do 36 divided by 3 plus 9x divided by 3. So make sure you distribute it to each term so it looks like this, and then you just simplify. 36 thirds is 12, and 9x thirds is 3x. 9 divided by 3 is 3. But be careful, because when I have a bigger number in the denominator, I have to be careful here. 3 divided by 18 is not the same as 18 divided by 3. So 36 divided by 18, okay, is 2, this 2 over here, and 3/18 is 1/6. So I have 2 plus 1/6 times x. That's also the same as when I have 3x over 18, I can just simplify. 3 divided by 3 is 1, and 1 times x is x on top. And on the bottom, 18 divided by 3 is 6. So these two expressions are exactly the same thing. Taking a sixth of the number is the same thing as the number divided by 6. And I was just trying to show you that these are not the same. I cannot flip it upside down and get the same answer. 18x divided by 3 is 6x. 3x divided by 18 is x over 6, or a sixth of x. And then I was just trying to get you to see here that this still means 36 divided by 18 and 3x divided by 18. Same thing. All right, and then I had you practice some. 12x plus 18 divided by 2. You guys did it very well. This was 6x plus 9. And then 2x plus 18 divided by 6, 1/3 x plus 3. And then you tried some yourself. I think Felix came up and wrote this one down. Negative 7 times 2x is negative 14x. Negative 7 times negative 5 is a positive 35. And then he simplified this one. 30 divided by 10 is 3. 2x divided by 10 is 1/5 of x. And then you have a little bit of homework practice in your book. And then you had 2 days this week, so by Sunday night, okay, you need to have a total of 3 hours this week and 15 topics. And that's it. Happy Halloween!